This lesson is on IV characteristics. Now, IV characteristics are graphs, and different electrical components have different IV characteristics and different shapes of graphs, depending upon what happens to their resistance as the current specifically changes. So the first component we've already kind of thought about when we looked at Ohm's law, which is what happens to a metallic conductor or a fixed resistor, which would be exactly the same when the current and voltage is increased. So just to explain the experiment, what we do in this is, and you will do this in class at some point, is that we will vary using a variable power supply, using a power pack effectively, the EMF. So we will vary the EMF, that's the thing we change. And we're going to measure two things about our component. So we measure the potential difference across our component, which is really what is plotted here. So this is the potential difference on this graph. And we'll also measure the current going through it. And that's very simple, that's the experiment we do. Now if you do this for a metallic conductor or a fixed resistor, you get a straight line through the origin. Now you'll understand why I've included negative values on here in a second, but you'll just be a straight line through the origin because the resistance is fixed in both cases. And remember, the gradient of this line is 1 over resistance, so effectively the same thing. Because it's fixed, it's a straight line. Now just to clarify, if I had a fixed resistor or a wire that had a bigger resistance, well, if the gradient of this line was resistance, then obviously the gradient will get steeper. If since the gradient is equal to 1 over the resistance, it actually gets, as the resistance increases, shallower. So this would be, for example, a higher resistance than this point. That might be because I have a different material or a higher fixed resistor value or a longer wire, or even that the temperature of a wire might increase and therefore the resistance would increase. So a little bit counterintuitive. Remember, the gradient is 1 over resistance, and so as the resistance increases, the gradient gets less steep in terms of the relationship between resistance and the gradient. So it would be a straight line, but the bigger the resistance, the steeper this is. Okay. Another way, a simpler way of thinking about this might be that if you have a really high energy, a really high voltage, but you have something that has a really high resistance, the current still is not going to be very big, and that's why this line is lower than this one. So that's the IV characteristic for either, in this case, like with a wire, we have a metallic conductor, which is a fancy way of saying a wire, or we have a fixed resistor. So the next one that we want to think about is bulb. Now, the key relationship to sort of explore with this, which we will come back to in a later lesson, is when we think about electrical power, specifically when we think about power loss, it depends upon only two things: the current, specifically the current squared, and the resistance. And so if the current increases, that will increase the amount of power loss. And if the resistance increases, so too will the current. If the resistance increases, the current will decrease. So they're inversely proportional to each other. And that's important to understand. So if I increase my current, the consequence of that is usually going to be that I'm going to get more electron-ion collisions, therefore more transfer of kinetic energy, therefore an increase in temperature. And temperature, if you think back to factors that affect resistance, will cause a direct increase in resistance. So if the current increases, that will increase the temperature, which will therefore increase the resistance. Which will then have the effect of, as the resistance now begins to increase, the amount of current that can flow is going to, as a result, decrease. So it's like a cycle, almost. So think about this in terms of a bulb. If I was to increase the voltage across a bulb, it will get brighter and brighter, it will get hotter and hotter. So as the current begins to, as it gets hotter, the resistance will increase, and that then causes the current to decrease. Okay, so this would start with a bulb the same way. You'd get a straight line where voltage is proportional to current. As it starts to get hot, the resistance starts to increase. Remember, that means the gradient gets less steep. So it will start to curve until the resistance becomes so hot the current can't increase anymore. And the same thing would happen if you had the current flowing in the opposite direction. Now, so this is the IV characteristic for a bulb. And the key to explaining this is that as the current increases, temperature increases, and therefore the resistance increases, and so that gets less steep. That would have the consequent effect of then reducing the current at a later point, or at least the change in the current. The two other IV characteristics you should be aware of are for a diode or an LED, which is just a type of diode, and a thermistor. So first of all, if we think about a diode, now I said I'd come back to why I've included the negative values on here. Current, when we talk about a negative value in terms of current, all we mean is that it's flowing in the opposite direction. That's what we mean. So for a wire, the wire doesn't really care which way the current flows through it. It will behave the same way. And as does the bulb. The bulb doesn't really care. But a diode, remember, only allows current to flow in one direction. So it does care. And so does an LED. So in the negative direction, the current will be zero. There won't be a current because it just does not flow in that direction. And then diodes all require, or an LED require, a minimum voltage before it starts to work. And then at this point, the resistance decreases massively. And remember that resistance is inversely proportional to the gradient. So if the resistance is decreasing, our gradient's going to get steeper. And so we get a curve like so. So this is our shape for an LED or diode. So it's negative. It's at 0 in negative, because at this point we pretend that resistance is like infinite. It's got a ridiculously high value, and as it gets past a certain voltage, the working voltage of the diode, then the resistance decreases hugely, and it just allows the current to flow through. Now a thermistor is related closely to the bulb, but obviously it works in the opposite way. So remember that the key idea of a thermistor is that as temperature increases, resistance will decrease. It will do the opposite of what a normal wire would do, which we talked about here, because a bulb just does contain a normal wire. So it does the opposite. So remember, if the resistance is decreasing, like it is here, the gradient gets steeper. So instead of this being a curve this way, a thermistor curves this way. And so the curve goes up. So obviously as it gets hotter, the resistance gets less and less and less. So you can see that this is like the opposite of the shape that you have for a bulb. So these are the 4 IV characteristics you should be familiar with. Remember that the resistance is inversely proportional to the gradient because the gradient is 1 over resistance. And so the steeper the line, the lower the resistance. and you've got your 4 basic shapes, and you should also be able to describe the experiment that we would do in order to calculate these IV characteristics.